Hydrogen is the most common substance in the universe, consisting of one proton and one electron. Given that hydrogen has existed since the universe began, this suggests that both protons and electrons are stable. However, are they? If the proton could decay, that behavior would have profound consequences for the future evolution of the universe, and it would overturn our understanding of the laws of nature. Somehow, this seems like something scientists should look into. Experimental, high-energy physicists like me spend our times making all sorts of particles. That's what we do. But most of those particles are unstable and decay into lighter ones. Because those particles decay, they don't stick around very long and consequently have very little to do with the familiar world around us. However, not all particles are unstable. The proton, neutron, and electron of the atom are well-known inhabitants of the world we experience. We know that neutrons can decay under the right circumstances, so we can ignore them in any conversation about long-term stability. But the proton is a much more interesting particle to consider. It's because of two things. First, our best theory says that protons are 100% stable, meaning that they won't decay. By the way, the name for that theory is the Standard Model. On the other hand, other theories predict that protons will decay, at least eventually. Some scientists hope these new theories will replace the Standard Model, so it's important to look for proton decay to see if these new ideas are on track. So first, let's see why the Standard Model claims that protons are stable. It all comes down to things called conservation laws. Conservation laws state that there are some properties that never change, no matter what. Three specific conservation laws are important when talking about proton decay: electric charge, energy, and a more obscure quantity called baryon number. Electric charge is pretty familiar. Conservation of charge simply means that after the decay, the amount of electric charge must be the same as it was before the decay. Conservation of energy has a number of implications, but the key one is tied to Einstein's equation E = mc squared, which says that energy and mass are basically the same. For particle decay, energy conservation just implies that particles can only decay into lighter particles. Baryon number is much less familiar. Baryons are particles consisting of 3 quarks. Quarks are one of the smallest known building blocks of matter, and protons and neutrons each contain 3 quarks each. Thus, protons and neutrons are both baryons, but there are many kinds of baryons. Baryon number is simple. Every baryon has a baryon number of +1. Antimatter baryons have a baryon number of -1. And to find the total baryon number, you just add them up. For instance, at the LHC, when you smash 2 protons, each with a baryon number of +1, the collision has a baryon number of +2. After the collision, no matter how messy and complicated, the baryon number is still +2. So there have to be 2 baryons wandering around somewhere in the debris. According to the Standard Model, baryon number, electric charge, and energy are all conserved. There are many more conserved quantities, but let's just focus on these 3. Let me give you an example. In the case of neutron decay, what happens is the neutron turns into a proton, an electron, and an electron antimatter neutrino. Since both proton and neutron have baryon number of +1, baryon number is conserved in the decay, +1 before and 1 after. Since the neutron has 0 charge, the proton has +1 charge, the electron has -1, and the antineutrino has 0, we see electric charge is conserved. It's 0 before and 0 after. And on the energy front, when we add up the mass of the proton, electron, and antimatter neutrino, they all have a total mass less than the neutron. That means neutron decay can proceed as far as these 3 conservation laws go. Now let's think about proton decay. To do that, we need to introduce two particles that are well known to particle physicists, but are not common knowledge. The first is called the positron. The positron is the antimatter equivalent of the electron, and the positron has +1 charge, just like the proton. The positron is also much lighter than the proton, like 0.05% the mass of the proton. Because the positron isn't a baryon, it has a baryon number of 0. The second is called a pi meson. It is also pretty light, with a mass of about 15% that of a proton, and it's not a baryon either, so it has a baryon number of 0. Finally, there's one more fact that's important, which is that the proton is the lightest baryon. All other baryons are heavier than the proton. So let's consider proton decay. The standard model says that any decay has to conserve electric charge, energy, and baryon number. Thus, a proton with a baryon number of +1 and a charge of +1 and a fixed mass would have to decay into some number of particles that would have to have a total mass less than a proton, a total charge equal to +1, and at least one baryon. But here's the problem. The proton is the lightest baryon. Thus, any other baryon into which it would decay would be heavier than the proton, and that would violate energy conservation. Therefore, because there's no way for a proton to decay into another baryon of higher mass, protons can't decay into another baryon. And, coming full circle, according to the standard model, the proton is therefore stable. That's it. The end. However, in some proposed replacements of the standard model, some of those conservation laws are relaxed. For example, these models often say that a proton could decay into a positron and a pi meson. We see that in this decay that charge is conserved and the mass of the particles after the decay is smaller than before, so the decay is okay on charge and energy grounds. On the other hand, we see that before the decay, the baryon number is +1, and after the decay, it's 0. So this decay is forbidden in the standard model, but it's allowed in some possible replacements of the standard model. Thus, observing this decay would be an important validation of new physics theories. On the third hand, we know that protons don't decay very much. If they did, atoms wouldn't exist and we wouldn't be here. Luckily, these new replacement theories say that the lifetime of the proton is very long. Even back in the 1980s, when these theories were new, predictions for the lifetime of the proton were about 10 to the 31 years. That sounds like a lot, but it's more than that. The universe has been around for 14 billion years. To simplify things, let's call that 10 billion years, or about 10 to the 10th power. That means that the shortest predicted lifetime of the proton is about 10 to the 21 times longer than the universe has existed. 10 to the 21 is a sextillion. So if you have a single proton and watch to see if it's going to decay, you're going to have to wait a very long time. But particle decay is a statistical process. It's like people. While the average lifespan of people might be 75 years or something, an unlucky few will die young. The same is true of protons. If you have enough of them, some will decay early. If you do the math, you find that 30,000 metric tons of water contains something like 10 to the 31 power protons. So scientists did just that. They built the Super K detector located in Japan. It's a cylindrical tank buried a kilometer underground, or about half a mile. The tank is about 40 meters tall and across, or about 130 feet in both directions, and it's full of ultra-pure water. In 1996, the Super K scientists turned their detector on and started looking for decaying protons, among other things. While they've made a lot of neutrino measurements, they haven't seen a single proton decay. From that, researchers have concluded that if protons decay into positrons, the lifetime for that decay is more than 2 times 10 to the 34 years. So, does that mean that protons don't decay? Well, no, we can't say that. All we can say is that they don't decay quickly into positrons. We need to build bigger detectors to see if protons decay with a lifetime longer than that. And we also need to build detectors that look for other forms of decay. And At Fermilab, we're doing just that, well, sort of. Fermilab is building the Deep Underground Neutrino Experiment, which we call DUNE for short. The primary reason DUNE is being built is to study the behavior of neutrinos. I made a video about the DUNE experiment. The link is in the video description. However, the DUNE detector will be huge. When completed, it will comprise some 70,000 tons of liquid argon. While for technical reasons not all of that will be available for looking for proton decay, the DUNE detector represents some 20 to 30,000 tons of useful protons. And with all those protons in such a super sensitive detector, scientists will be keeping an eye out for proton decay. There are lots of different theories about how protons will decay. I've mentioned the possibility that a proton will decay into a positron and a pi meson, and while the DUNE experiment will be able to see such a decay, the experiment has spectacular capabilities to look for the possibility that a proton will decay into a positively charged meson along with a neutrino. The DUNE experiment will identify that form of proton decay with excellent efficiency, and that's great news, as the water detectors aren't as sensitive to that particular decay mode. Of course, DUNE will also be looking for other possible forms of proton decay as well, but it's the K meson channel that DUNE dominates. It will be a huge scientific advance if it's seen. Long term, it's expected that the DUNE experiment will be twice as sensitive as the competition. Will DUNE see proton decay? I know how I would bet, but the simple truth is, I don't know. That's the thing about research. You don't know the answer until you find it. DUNE is going to be super busy doing neutrino studies, and the proton decay research will be conducted in parallel. Given the implications of seeing proton decay, Fermilab scientists are on it, and one day, we'll know. Okay, so proton decay, if it exists, is a super rare process and one that's very hard to measure. But that's okay. If it were easy, everyone would be doing it. If you like learning about possibly paradigm-shifting measurements, please like the video and subscribe to the channel by smashing that button down there. Come on, you know you want to do it.